let's talk about energy. Energy is defined as the ability to cause change. It's a scalar quantity. It's measured in joules, just like work was measured in joules. And please note that it is a scalar quantity. It's not direction aware. Uh, can show up in a lot of forms, and the pictures on your handout we can define these different forms. Uh, First one here, light bulb is representing electrical energy. Next one here is representing chemical. The guy by the heater representing thermal energy. And last is the sun representing solar energy. One of the other forms of energy that we define in physics is kinetic energy. And kinetic energy is pretty basic. It's the energy that's associated with moving objects. Okay, if object's in motion, it has kinetic energy. The equation for kinetic energy, we represent kinetic energy with a KE for kinetic energy, and that's equal to 1/2 of the object's mass times its velocity squared. So velocity plays a role in it, mass plays a role in it, and we take 1/2 of that, and we get our kinetic energy. Uh, Another way to write this equation would be mv squared over 2. It's mathematically the same. It's just a matter of preference of how you want to calculate. So if this is nicer to look at for you, go ahead and do that. If this equation is nicer to look at for you, fine. But this is how we calculate kinetic energy. One of the things that goes along with kinetic energy is the work energy theorem, and it's the idea that work and energy are related. Uh, and the reason why they're related is because energy gives you the ability to do work. So you'll see this work energy theorem represented like this. This stands for work. Okay, work is equal to however much the kinetic energy changes. So the change in kinetic energy, and it's equal to work. Uh, this equation will get expanded upon when we do conservation of energy. So uh, this is a nice little tool we have for what we call rigid objects. Rigid objects that are moving. Uh, and it doesn't factor in something that we'll get into later, which is potential energy. So this, again, this is the work energy theorem, and it's nice because when we have a moving object, we can figure out how much work it's doing or how much work is being done on it uh, with this work energy equation. Simulation I want to show you here is 3 cars here, and you're going to see that the initial speed of the green car is 10, 18, I'm sorry, 10, 20, and 30 are the speeds of each of these cars. And if the green car has 10 uh, meters per second of initial speed, 20 meters of initial speed for the red car, and 30 for the blue car, we can figure out how much kinetic energy they have. And what this simulation is doing is showing the skidding distance of each car. So how much they're assuming that they're under the same friction conditions, and they begin their stop at the same time, and you can see what's happening to the distance, and I'm gonna show you why that is. And we're also going to first off, we're going to need to calculate what the actual kinetic energy is of each car. The red car, the green car, the red car, car and the blue car. So we can figure out how much work is required to stop each of the cars if they have the same mass. Okay, they all have the same mass. We're going to assume they have 1750 kilograms of mass. The green car is going 10, red car is going 20, blue car is going 30. Okay, so we know that work is equal to our change in kinetic energy. Okay, so this is our main work energy formula, and let's see what we can do with it. Change in kinetic energy is simply whatever the final kinetic energy is minus the initial kinetic energy. Well, that's final kinetic energy minus initial kinetic energy. And we can expand on this equation further and say mv v final squared over 2 minus mv initial squared over 2. And we can figure out how much work is required to stop the car. Now it's just a matter of plugging in numbers. The nice part about all of these objects is they're all going to stop. So the final velocity is all going to be 0. So this term's going to drop out and be 0. Minus mv initial squared over 2. So if we can figure out the initial kinetic energy of each of these cars, we can figure out how much work is being done. For the green car, we've got 0 minus 1750, that's the mass, times 10, which is the velocity in meters per second, squared, divided by 2, and we get minus 87,500 joules. That's to stop the green car. Why don't you go ahead and calculate the red and blue car, pause the video, calculate the red and blue car, see if you come up with the same answers that I come up with. So the work to stop the red car, 350,000 joules, negative 350,000 joules, and the work to stop the blue car, negative 787,500 joules. Coming back to this video, if you look at the distances, the skidding distance, we've got 5 for the green car, 20 for the red car, and 45 for the blue car. That's 5, 20, and 45. So I've written those numbers down, 5, 20, 45. And if we look at the relationship between the stopping distance, or if we think about work as force times distance, remember work is just force times distance, or displacement, so that comes there. And if it's equivalent to some form of kinetic energy, mv squared over 2, you can see as the velocity goes up, okay, if we think about what the velocity of the green car was, the velocity of the green car was equal to, what was the velocity of the green car? It was 10. The velocity of the green car was 10. The velocity of the red car was 20. So as you double the velocity, how much is your stopping distance going to increase in this case? Well, it'll increase by the square of the factor that the velocity went up by. So it should go up by 4. We have 30, so the velocity is going to go up by 3 for the blue car by a factor of 3. 10 times 3 is 30, so it went up by a factor of 3. So the stopping distance should go up by a factor of 9, and it does. Okay, that's the relationship between velocity and the stopping distance, and that's what this simulation is showing you here. And if we look at the work, we can see that the proportionality works with work as well. we're increasing the velocity by a factor of 2. Work is going up by a factor of 4. How do we know that? If you take 87,500, multiply it by 4, you're going to get 350,000 joules. Same thing uh, with the blue car. That went up by a factor of 3. So work should go up by a factor of, the velocity went up by a factor of 3, so the work should go up by a factor of 9. 87,500 times 9 is equal to 787,500. Last example we're going to do is, we've got 4 cars here, and we want to ask the question which one has the most kinetic energy. Uh, so, why don't you go ahead and calculate each of these. Take note of the velocities and how they're represented, and think about which one you think initially is going to have the most kinetic energy, and then calculate. Again, we're just calculating kinetic energy. So, kinetic energy is equal to 1 half mv squared, or mv squared over 2. Let me rewrite this. Kinetic energy equals mv squared over 2. So we're just calculating the kinetic energy. We're not saying there's a change. We're just saying, hey, this is how fast it's moving. This is its mass. What's its kinetic energy? And which one of these 4 has the most? And go ahead and calculate and see if you come up with the same answers as I do. After you've calculated, you should get kinetic energy for the first car, car A, 99,900 joules, car B, 343,000 joules, car C, 749,000 joules, and car D has 237,000 joules of kinetic energy. Interesting thing to note is that car C was actually the smallest of the 4 cars, and yet ended up with the largest kinetic energy. And the reason for that, and hopefully you converted your velocities from miles per hour to meters per second, from kilometers per hour to meters per second. Uh, if you didn't, you should do that in order to get a unit of a joule. But anyway, backing up, car C has the smallest mass, but it's traveling at the highest velocity. Okay, so that's what gives it the highest kinetic energy. So it's much more efficient. If you want to change something's kinetic energy or make give something a higher kinetic energy, increase its velocity before you increase its mass. Because if you look at car D, that's the heaviest, or excuse me, that's the most massive of the 4 objects. But because it's not moving at a relatively high rate of speed, it doesn't have the same velocity as car B and car C. Now, it is moving higher at a higher rate of speed than car A, and is predictably going to have it has not only a higher mass and a higher velocity, not only has a higher mass, but it also has a higher velocity. So predictably, it's going to have a higher kinetic energy than car A. So understand how mass affects kinetic energy, and understand how velocity affects it exponentially.